Broadcast is now starting. All attendees are in listen-only mode.
Good morning or afternoon, and welcome to the first Pavement ME User Group software training webinar. I'm Kelly Smith with Applied Pavement Technology, and on behalf of the Federal Highway Administration and the rest of the project team, I'd like to thank you for joining us as we deliver this training presentation on Pavement ME design. The topics for today's webinar are on the design of AC overlays on existing asphalt pavement, existing concrete pavement, and fractured concrete pavement. Next slide, Prashant. So this webinar is being conducted as part of the FHWA contract in support of the Pavement ME User Group. As many of you know, the User Group project has been led by Jen Albert and Chris Wagner and Tom Yu at FHWA with financial support from several agencies participating in the TPF 5305 pooled fund. I should also point out that the webinar is being conducted under the user group contract are separate from those being sponsored by AASHTO and the Pavement ME Task Force and conducted by Harold Von Quinnis and the ARA staff. But these webinars that we're doing, they provide additional training opportunities and are designed as extensions of the training that we provide in the user group meetings. Next slide, Prashant. The topics for this webinar were identified as being the top of the interest list among the TAC member states and are certainly the types of designs that many states commonly perform. Dr. Linda Pierce from NCE will provide the training for the first two topics, and Dr. Julie Vandenbosch from the University of Pittsburgh will provide the training for the third topic. Each topic is going to be about 40 minutes long and will consist of about 30 minutes of presentation and 10 minutes of Q&A. And I'd just like to quickly recognize and thank Justin Schenkel from the Michigan DOT, Lydia Petticord from the Pennsylvania DOT, and Harry Nair from the Virginia DOT for providing the team with projects and data for developing these training demonstrations. Next slide, Prashant. So just a quick going over of the housekeeping issues, and many of you know Prashant Ram helped us through the Pavement ME User Group back into December, and he's going to be the man behind the controls, the GoToWebinar controls today for this webinar. I just wanted to point out that the audio input lines are muted and that this webinar is being recorded. If you have any questions or comments or other inputs that you'd like to submit, you can do that by typing that in the questions box on the control panel and hitting the send. We will address as many questions as possible at the end of each topic demonstration, and any questions that go unanswered in the webinar will be addressed and responded to by email in the days following the webinar. Also, the webinar recording and PowerPoint presentations will be made available at a later date through an email containing a link to their posting. I guess before we get into it, we have a couple poll questions that we want to put out to the group at this point. So Prashant, can you bring up the first poll question? So we'd just like to take a brief minute or so to get your input on these first two questions. So please take a moment to respond to the questions. And how's our feedback coming, Prashant?
We have about 65% responses. There's a little bit, we're going up and slowing down right now, but I'll give it maybe 10, 15 seconds and then shut it off.
Okay. All right. And there we have some of the results. We're not going to really talk about the results too much. We just want to kind of put the questions out there and get a sense of where everybody is with some of these designs. Can you bring up poll question 2, Prashant? So again, take another minute or so to respond to this question. How's our status, Prashant?
We are at a 72% response rate. Some more responses coming in. I'm going to give it 10-15 seconds and then shut it off.
All righty.
Almost at 80% now.
Excellent. Well, thank you for the feedback. And I guess at this point, we're going to move on with the webinar, and I'm going to turn things over to Linda Pierce, and she's going to talk about AC overlays on existing asphalt and composite pavements. Linda.
Great, thank you, Kelly. Get the right monitor here. All right, okay, so as Kelly noted, I'm going to shut my webcam off here to keep my speed up. We want to talk about the rehabilitation designs of asphalt overlays today. And in Pavement, the design options are for existing asphalt, existing fractured concrete pavements, existing intact concrete pavements, and then there's others. And so as Kelly noted, we're going to spend some time today just going over the existing asphalt overlay of an existing, or an asphalt overlay, sorry, of an existing asphalt pavement or a flexible pavement. Julie will hit on the crack and seat rubberization, and then in the next session, I'll hit on the overlay of an existing composite pavement. Seal coats and overlay interlayers, we are not going to discuss it all today, so that'll have to be maybe another session. All right, and so as Kelly also noted, we'll have to thank, at least for the example that I'll be demonstrating today on asphalt overlays of an existing asphalt pavement, is based on information obtained from Harry at Virginia DOT. And for both this session and the next session that I'll be presenting, it is based on the information provided. And probably one of the big things when we received the files from the DOTs, there was a version difference. My company only has version 2.6, and both of the Virginia and the next example were based on an earlier version, and so I had to unfortunately still use the material property information from the DOTs, but I had to switch back to the global calibration values just to be able to run this example. And so again, the example I show you is based on an actual project, but the calibration coefficients are globally, and so there may be differences than what the DOT would actually see. So Harry, don't be too surprised at the results that you'll see on this analysis or this demonstration that I'm showing. All right, so the project is on a four-lane divided rural interstate. And again, as I said, the modifications had to go to 2.6. The climate location was slightly different. We were having a couple of challenges in getting the original climate file to load. So we picked one that's close, and then of course, as I said, the global calibration factors are slightly different. All right, so the typical road configuration, you can see, got a little bit of centerline cracking. There's looks like some fatigue in the wheel paths. going through and just kind of saying this is, the typical layout of the road, just to give you that perspective. The distress prior to the overlay, so the overlay was conducted after 2010, and you can kind of see here, IRI is the circles, where rut depth is the triangles. So looking at a little bit of variability in data collection, but that is something that we also kind of know the reasons for some of that variation. Pretty much really good IRI, holding in the 80s, in the high 70s, low 80s. The rut depth, at least in 2010, we can say, hey, is about a 1500ths of an inch. So a little bit of rutting right is still pretty good, but certainly the issue now becomes alligator cracking and the presence of transverse cracking. And again, alligator in circles, transverse cracking as the triangle shapes. And again, you can see a little bit better trend here in the results, but showing that in 2010 there was a little bit more than 15% alligator or fatigue cracking and about 3,000 feet per mile of transverse cracking. So again, predominant distress for this case is cracking, more so than rutting. All right, now what I'm going to do is go through and demonstration of software during a webinar, as you know, is just a failure. And so what I'm going to do is go through and do screen captures and try to demonstrate the process through screen captures. And so hopefully that'll be good enough information that you guys can actually follow along. And I'm just going to kind of tumble through PaveME inputs, top to bottom on the left-hand side of the input screen. So certainly the first one is just to show that, hey, we're going to go and do an overlay of an existing asphalt pavement. Design life is 15 years. The original was built in '78. And then we're going to do construction was in June of 2010, with traffic loading of September of 2010. The existing pavement, as you see on the right-hand side, we've got some overlay thickness. We've got 12 inches of existing asphalt, 8 inches of an aggregate base, 6 inches of a fill material that has a CBR of 30, and then an A76 AASHTO subgrade classification. As far as performance criteria goes, we got initial IRI of 63 inches per mile with a terminal of 140. Then you can see the fatigue cracking, top down, bottom up, the amount of thermal cracking, deformation, or total rutting is a little bit more than a quarter of an inch, with the majority of that happening within the asphalt layer, or being limited to the asphalt layer. And then total reflective bottom-up cracking is at 25%, and then total transverse cracking, thermal and reflective is at about 2,500 feet per mile. And again, as is classic, you can set the reliability, except for bottom-up fatigue cracking and thermal cracking, that is set at 50% reliability. All right, so the traffic screen, and I'm not going to bore you too much with all the details, but I will kind of show you the information that was included for this design, and we'll kind of blow them up as we go through, just so you can see it a little bit easier. So the two-way average annual daily truck traffic is at about 11,200. Number of lanes in each direction, or in the design direction, I should say, is 2. The percent of trucks is 50%, and then 90% of those in the design lane with the operational speed. And for this case, the traffic capacity was not enforced. I believe on the right-hand side, the configuration, the wander and the wheelbase is pretty standard. I believe they're all default values that were selected for that, so probably nothing too exciting to change there. But certainly, if you have a specific or a special loading case, that certainly can be modified. The distribution of vehicle class and the growth rate, again, I think it's just taken from the traffic information, and then the DOT used a growth rate of 0.7% compounded over the life. For this one, it's I think this is the kind of the classic for most interstates. It's pretty even, January through December, for class 4 through all the classes, class 13 here in this case. So that was just I think pretty typical for an interstate. There really isn't a monthly adjustment that I think most DOTs do not see on some of the higher class routes. Then of course you have to be able to have your axles per truck by vehicle class, single, tandem, tridem, and quad. And again, these are taken from the traffic studies or the traffic information that the DOT contains or collects, and so I'm part of the traffic database for sure. All right, the climate, and as I noted, we had to change the climate slightly, and so we went ahead and picked the location, and certainly when you in the program, this is a series of pinpoints that you can go through and select, and this is just the location of this particular project, noted by that little flag over the location of Virginia. As far as the AC layer properties go, there's a number of them. Certainly going in and doing an interface, doing the endurance limit, whether you include it or not. And at least in this example, we did not use the endurance limit, but you do have to go through in the AC layer properties location and identify the rehabilitation level. And so you actually get a couple of choices. Certainly you can go level 3, level 2. Level 3 gives you much more of a general condition, where you go level 2, you can actually get into more specific details of the presence of distress. So both of them have the ability to include the mill thickness, which in this case we use 2 inches. They also have the ability to put in rut depth, so went ahead and can do those regardless. But certainly where they differ is in this structural rating, environmental rating versus actual distress. And if you've got the data, it is always best to use it. And so we would proceed forward in this design example. Oops, sorry about that. Using the level 2 analysis, and so that would be the case. And I know supported by at least all the discussions we've had in the user group meetings. If you have a higher level of input, go ahead and use that if you feel comfortable with the information contained in your database files. All right, getting into the AC layer properties. Again, a lot of this information, hopefully, if you've got it contained in your materials database, that's been transferred over, and so we can go ahead and use that from the Virginia file that we were sent. We had all that information, and so we'll go through kind of the inputs a little bit one by one, but much more in general. Again, I don't want this to be an exercise of entering data into a spreadsheet, so or entering data into the software. So we'll just kind of hit the highlights of what was used in this training module. All right, so as many of you know, you go ahead and double click on the layer in question to be able to edit it, and then that brings up the screen or the tab where you can see what your thickness is. You can worry about your mixture, your mechanical properties, and then your thermal properties. Certainly the aggregate parameter allows you to input your sieve sizes on the 3/4 to 3/8, the number 4, the number 200. Going down for the super pave or the level 1 on the mechanical properties, you can go in and if you have that information, put in your temperature, your binder, G-star, as well as your phase angle. Same with creep compliance. You can load in that amount of information. Similarly with the dynamic modulus, you can go in and put that information. And for both the creep compliance, dynamic modulus, you can change your level of input. So if you put these into a level 3, it'll change that top. I don't think you guys can see my cursor, but it'll change that top defining point from level 3 super pave to a level 3 when you change your dynamic modulus and your creep compliance back to those values. And certainly the indirect tensile is the same. You can either go in and use a level 3 input, or you can use the G-star based model. but however, it's not been nationally calibrated. So I know that for the most part, a lot of agencies are using the viscosity-based, nationally calibrated model. But you have that ability to change that, to change the reference temperature, and that type of information if so needed. And this is just a summary. Again, I didn't want to go through the layer properties for both the asphalt overlay and the existing, and so I really just summarized it here on this table. That kind of shows what was used for mixture, volumetrics, the mechanical properties, and the thermal, both of the overlay, what I just ran through, but then certainly on the existing, and have that information. And I think probably here the key is the air voids on the existing slightly lower than what was used in the overlay, same as the effective binder content. And then for the existing, it was a PG 6422 for the asphalt binder. But then everything else is pretty much very similar. And again, the thermal properties are the default properties used in this case. All right, similarly, when you go through, double clicking on the base and the subgrade layer properties, looking at probably here, the modulus is of interest. And there you've got the option, again, you have the opportunity of going input level, but for input level 2, you can go in and go ahead and select your type of material or type of evaluation, be it resilient modulus, CBR, R value, and then put in that value for that particular method. Certainly you can also go in and change or select your gradation. And again, putting in the gradation, the liquid limit, the plasticity index, all that information. Or certainly you can do the level 3 and just go in and select, hey, I've got an A1 soil. Bring in all the information needed for the analysis. All right, similarly to the asphalt, I just went ahead and summarized the unbound and the subgrade and the base layer materials. So as we noted, the stabilized base or the non-stabilized base is 8 inches over 6 inches of fill over the subgrade. And then you can see the unbound coefficient layer of earth, lateral earth pressure, Poisson's ratio, modulus, and sieve soil type for each one of those layers. All right, I always, this is just from the output from the PaveME PDF file. And I just I chopped out the middle piece, which talks about the asphalt binder, because I really like to make sure when I go through and actually do a design, did I put everything in right? So I really do look at this particular output from the program just to make sure that, yep, I did put in 2 inches of an overlay, and yep, the existing's 8 over 6 inches of the fill material. I always like to look at the heavy truck traffic as well, again, to make sure that the values that I thought I input is actually what I input. But it's always interesting to me to see the impact of the heavy trucks over the time period. It's always surprising how quickly 15 years of traffic accumulates. I'll have to say I still miss easels, but I know that the switch to heavy trucks is happening, but it's certainly slow, at least for me. All right, so what I wanted to go through is kind of evaluation scenarios. And again, I think what is intriguing about PaveME certainly is the process it goes through, the whole mechanistic empirical. But I think, what do you do with the output, right? Is it just something that hopefully everybody's getting a good sense, getting a good feel for the impact of changes to designs and how that influences performance. But also it's something that hopefully you're not working in a vacuum. And if PaveME comes back and says you need 17 inches of asphalt, maybe you're kind of doing that little data check on maybe that doesn't quite pass the test. So rather than get into a lot of the specifics of software operation or the workings of the verification, calibration, the model development, what I really wanted was to highlight, so what are the results? What do you get if you go through different types of scenarios using the PMED for evaluation of any given project? But for this one, the file that we received from Virginia It was a 2-inch overlay, or a 2-inch mill and a 2-inch overlay. So pretty much just a mill and fill type of an operation. So I said, okay, let's see what's the impact of no milling with an overlay. What's the impact with mill and fill? And then I'm going to vary the thickness of the overlay on that one as well. And then binder, I think, you know, it's always interesting. We always have to be careful with binder because we know the database that was the LTPP database didn't have everything that we would have hoped, but certainly being able to see and assess what type of influence the asphalt binder has on some of the results, you know, is always intriguing to me, at least. You know, coming from a DOT that always had a standard grade of binder, and then when PG came in, it's just like, you know, I see there is a benefit in using some of the more modified binders, but again, knowing full well that maybe they're not as well quantified as much as we would like them to be. So always have to have a caveat with everything related to some of the things that we have to evaluate. All right, and so here again, I'm not going to drag you through all the various database or the various tables and graphs that are populated in the output of the PMed runs. So I'm really just going to focus on the condition, the target value that we used in the analysis, and then there's going to be a series of columns that get added to this table that kind of demonstrate the evaluations that we did. And again, just to remind you that we're looking at 95% except for the bottom up and fatigue and thermal cracking, where we used the 50% default value. All right, for the 2-inch overlay where we did no milling, certainly the IRI fails to meet the criteria. But I also would have to say that we, you know, and I know Harold has said this many a times in our past meetings, don't change your overlay thickness because you're trying to meet IRI. And I completely and totally agree with Harold on that. It's certainly, again, there isn't a performance-based information in PMed. Certainly, they had to make hopefully, as many of you remember, they had to make a lot of assumptions in being able to predict IRI. And I guess my other comment too would be that, you know, Virginia had great IRI on this road prior to the overlay, and even though their target is 140 in their design process, we didn't see that type of effect on the previous road. It was maintaining a pretty low IRI, you know, throughout the process. So that's, again, I think you always have to take IRI with a grain of salt before just saying, yep, I got to make my pavement thicker, or I've got to change something to meet IRI. So always be leery with that one. Unless, of course, it's related to cracking, you know, right? So if we know that you've got your bottom-up cracking, your top-down cracking, your reflective cracking is all, you know, off the charts, certainly your IRI is going to be off the chart as well. So there is that connection. So just be mindful of how the distress types relate each other and how the assumptions are made within the software. So at least for this, the 2-inch overlay and no milling, the rut depth is fine. You're still well below as far as the rut depth of the asphalt layer, and certainly total wetting is still well within the target value. There is no bottom-up cracking. Top-down cracking is predicted to be about half of what the target value is, so it's looking really good there. However, the bottom-up plus the reflective, so this is really reflective cracking happening, is exceeding the target value. So you're getting 36% where 25 was the target, and so we failed the criteria there. Same with thermal cracking is doing great. However, and the thermal and the reflective cracking on this range is 2400 compared to the 2500 of the target, so all's good there. So now I say, okay, what happens if we go ahead and run the 2-inch mill and fill, or the 2-inch mill with a 2-inch overlay? Again, the same type of information. The rut on the asphalt layer gets up a little bit, but again, nothing serious. Still looking at top-down cracking is in good condition. Our bottom-up and reflective cracking has reduced a little bit. Was 36 with no milling, now it's 28% with a 2-inch mill. So getting slightly better. And then no change in thermal cracking and reflective cracking. Pretty much stays the same from what it was in the previous. So now I said, okay, what happens if we do a 2-inch mill and fill plus a 2-inch overlay? So take off 2 and let's put back 4 inches. Again, everything is not really changing as far as IRI goes, and we've done nothing to help with the bottom up and the reflective cracking. You know, so that mindset of, hey, well, if I can just add a little bit more thickness of asphalt, maybe I can help mitigate the reflective cracking. At least in this case, it really didn't have a significant effect on the level of reflective cracking that's happening in the overlay. And so I did the classic thing that we probably shouldn't always do. I said, well, what the heck if I make it thicker? So I'm going to go put down a 2-inch mill and fill and a 4-inch overlay. So our total of 6 inches of new asphalt on top of it. And I'm sorry, this slide's slightly different. This 23, now, I'm sorry, I'll take that back. You're still not making it on IRI, so it's still a little bit low. But again, I think with 2 inches of milling plus 4 inches of asphalt, the contractor has more than sufficient opportunities to improve your IRI. So again, I'm not really concerned about the IRI in this case. But the good thing is I have now reduced my amount of bottom up and reflective cracking. So I've gotten rid of the reflective cracking problem by going to a really thick overlay. And as we go through this, there's also absolutely no attempt to try to mitigate reflective cracking by doing something different. This is purely an exercise in asphalt overlay thickness that gets rid of that reflective cracking. And again, that's not maybe a cost effective. There may be methods that a DOT knows helps improve the reflective cracking or helps to minimize the reflective cracking. And so certainly those types of activities should certainly come into play rather than just automatically keep on increasing the asphalt overlay thickness to get rid of some of the distress types. All right. And this is just a caveat in the manual of practice that pretty much says, hey, you know what, LTPP didn't have, or the information obtained to develop the models used or the local global calibration were based on information that may not have shown that there was a difference. You know, so in the LTPP, there wasn't really much of a difference in performance, mill versus no mill. Using an inner layer, not using an inner layer, going through using a seal coat, not using a seal coat. And certainly if any difference does exist between a mill and a no mill situation in your agency, then those should be used in the calibration process. But going globally calibrated models did not show a difference. So I think that's where you saw that there was this, I had to keep on adding asphalt thickness to be able to assess the impact of milling really wasn't there by itself. But however, if your agency, your state sees a benefit in milling, sees a benefit in seal coats or inner layers in mitigating reflective cracking, then make sure that you actually have some type of a local calibration in those instances. All right. So with that, I also said, okay, well, let's go back and let's see what changing the binder grade has to do with it. And so I had to disconnect the level 1 material properties for the asphalt overlay. Since I don't have Virginia's material database, I said, it's okay, I'm just trying to demonstrate the difference rather than give an absolute value. So I went in, changed the inputs on the asphalt layer to allow me to put in a level 3 and put in the PG grade. So I did it for the PG 5822, and again, completely and totally ignore the comparison of the values I'm going to show at these tables with the ones that I just got done with changing the asphalt overlay, because it's an apple and orange or apple to orange comparison and really shouldn't be used. So try not to go, wait a minute, how come all my rutting is higher? Because it's different. It's a different process to do the evaluation. All right, so the PG58, and again, let's not focus on the IRI for previous reasons we already discussed, but do take a look at the total rutting. Now we got 0.36 inches, and the bottom up and reflective cracking, again, it didn't go away just because we changed the binder grade, so it still is pretty high compared to what our target was. Now switching over to, let's run the analysis with a 64 minus 22, and lo and behold, we do improve both the asphalt rutting. It's always been within the tolerance, but the total rutting now actually goes down slightly as well. And I guess, you know, the concern that I have in this is that the asphalt rutting is probably where most of the rutting is going to occur, but yet we're affecting total rut depth with a change in PG binder. Doesn't completely and totally make a lot of sense to me, but at least the reduction is because of the asphalt layer. So at least it's the same, right? So the asphalt rut depth and the total rut depth is the same, the decrease, and so, you know, you got to kind of remember that hey, it's, even though my asphalt rutting is still good, my total rut depth is still off, and so at least I'm not, my rut depth isn't changing because I changed the binder content, I guess is my point. So you still have characterizing some type of rutting in the base and the subgrade layers in this analysis, which again, I think if that's the case in your agency, that's fine, but I think for most cases, we're seeing that the rut depth is confined to the asphalt layers. So, all right, and then the PG going to a PG 70 minus 22, so we actually get another 0.03 inch reduction in the total rut depth, which actually we see as the reduction in the AC rut depth as well. So again, we do have consistency that it is only addressing the rutting that would occur in the asphalt layer. So that's again, that's a good thing. And we slightly changed the bottom-up reflective cracking, but again, we're not expecting a change in PG binder to actually stop some of the reflective cracking. So it by itself would not do that. So, all right, that was a fast whirlwind tour of the asphalt overlay of asphalt. Does anybody have any questions? Or Kelly, I should say, do we have any questions in the chat box?
We do, Linda. We have a few questions in the chat box. Let's start with the first one. Two questions kind of packed together about the existing HMA layer. You've modeled the example HMA as one layer, but there are almost always more than one different type of existing HMA layer present. So which layer do we use to represent the existing HMA layer?
Yeah, good question. You know, so, you know, I go back to a lot of my time and using mechanistic design is really trying to minimize the number of layers as much as possible. It's just a limitation to the whole mechanistic empirical principle. And so if you've got similar enough layers, being, you know, let's go based on maybe like resilient modulus or dynamic modulus of the asphalt layer. You know, it really takes orders of magnitude to have that make a difference. And let me turn my camera back on. To really have an impact on the mechanistic empirical process. And so if it's similar enough, I would combine them, and then you could actually go through and use an average type of a value of all layers. Now with that, if you happen to have an asphalt layer that was used with a PG binder, so relatively within the last 20-25 years, and it's sitting on top of a macadam, definitely I would not combine the macadam with the more recently placed asphalt layers. And so if there's a significant difference, go ahead and separate them, and if not, just go ahead and use the average value.
Great. And there's a second part to the question, Linda. It says, once that's determined, what are the inputs for the existing HMA? Do we assume new properties, a level 1, or guesstimate the existing using level 3 inputs?
For that, unless you'd have to go ahead and do, you'd have to probably use a guesstimate because you don't have a level 1 property for a combined layer, right? Again, if they're all similar, you know, so it's a dense graded PG 64 placed in 1980, and then you did a PG, it wouldn't be PG 64 in 1980 now, would it? But if they're similar enough, you can probably just use the one that's on top. But like I said, if they're different enough, and you're combining them, or they're dissimilar and you're combining them, I would just go ahead and use the average value, and you'd have to go level 3.
Okay, thanks. And I think the next question is probably one I can answer, but I'll let you tune in as needed. How was the existing pavement characterized structurally? I believe it's a level 2 analysis, wasn't that right, Linda?
I guess, Kelly, I'm not exactly sure what that question means.
If that's getting into the structural distresses, the cracking, fatigue cracking levels, and that would be structurally oriented.
Yeah. Well, yes. Okay. Yes, it was level 2.
Yep.
Yeah. I'm sorry. I should have made that clearer, but yes, it was level 2.
Yeah, because I know you pointed out level 2 versus level 3 earlier in the presentation.
Right.
Another question: what is the difference between bottom-up cracking and bottom-up cracking plus reflective?
Yeah, so bottom-up cracking is just fatigue at the bottom of the asphalt layer. So it propagates up. It's the classic fatigue alligator cracking type thing, and then the reflective is the reflective cracking of that distress. So it kind of differentiates between the fatigue cracking that propagates from the existing asphalt into the overlay, as well as the propagation of reflective cracking. For transverse reflective cracking as well. So it captures both fatigue as well as transverse cracking. Because the cracking below the new overlay is going to eventually propagate up. Of course, if the layer's not super thick, or you haven't done some other type of mitigation to stop the reflective cracking.
Great. Another question: the design example is being driven by reflective cracking, but Pavement ME doesn't address how much cracking remains in the existing surface after a 2-inch mill. If it's bottom up, Virginia's model isn't capturing it. If it's top down, it's probably removed anyhow. Comments?
Boy, I'd have to ponder that one for a minute. And figure out that. So if possible, if we could, Kelly, get back to that to that answer later.
Yeah,
that would be great. Like I said, I have to think about that one.
Yeah, we can certainly do that. Let's see. We may have time for one more question. For existing AC, does the binder PG reflect original binder construction, or the aged binder like that extracted from wrap?
So for boy, help me on this one, Kelly. I think it's characterized. The materials library is probably characterized on the new, and then it's aged within the software.
So that would be something that Virginia has done on their end to characterize that existing. Yep.
Right.
Okay. We got a few more questions, but again, in the interest of time, let's move on to the next presentation. I did want to say that, Linda, we forgot to do a poll question right before the start of your presentation on this, but what we'll do is we'll capture that in your next presentation here. So if you want to start off the next topic and do questions.
Do you want to do both poll questions next topic, or?
Let's do both poll questions. Are we ready with those, Prashant?
Yeah. Sorry about that.
So here's the first one. It should have occurred in the first topic, but approximately how many AC over AC projects does your agency perform annually using PMed? And again, one answer, certain ranges of responses. So let us know what your responses are on that. How are we looking, Prashant?
We have about 62% response rate. Maybe going to give it a few seconds before I turn it off.
All right.
And Linda, do you want me to do the next poll question right away?
Yes, if you could do the next one. I
Yeah,
believe it's
let's do that one.
on existing intact concrete. So this is the setup for training topic 2. And I'll just mention that we do have a few more questions on the first topic, but we will, like I said at the beginning, we will combine these questions and we will get responses together and get those responses off to the group following the webinar.
And I was just going to say too, Kelly, on that that last question concerning characterization of the existing, we might have to do a follow-up on that one too. So I'm thinking now that maybe the question is that they might not have had material properties. I think that original pavement was placed in 1978, so it's more than likely they might not have done all the extensive testing. So let me do a circle back on that one too, and we'll get back to everybody on the response for that.
Okay. And are we got some good response rates, Prashant, for that one? Are we ready to move on?
Yep, about 60%. Yep. Mm-hmm.
Okay. Back to you, Linda.
All right. Still see my screen, Kelly?
Yep.
All right. So now we're going to dive into asphalt overlay of an existing intact composite pavement. So we didn't do anything to the underlying concrete, and so it was an asphalt overlay was placed, and we're placing an asphalt overlay on top of that composite pavement. And similarly with the previous example, this one was from information provided by the Michigan DOT. All right, so here it's again, you've got now an urban highway type. It is a 4-lane divided, and again, the same type of comments on the modifications that we had to do to get the evaluation to work in the current version of PMED. Justin had provided us, the original file was based on version 2.3. We used version 2.6. So again, we had to do a slight change in the climate location, as well as we used the global calibration coefficients rather than the ones provided by Justin. So here's a shot of the pavement. This is on US 23. Again, you can see the existing has got a couple of shoulder, a narrower left shoulder, wider right shoulder. See the lay of the land, so to speak, and some of the existing condition of the pavement. Again, just another shot to kind of give you that perspective. The stress prior to the overlay was occurred, at least in 2019. The stress was this distress index that the Michigan DOT uses, looking at the IRI as well as rut depth. Rather than a year, I actually was able to get the information along the project, and we go from milepost 0.5 approximately to almost milepost 10. You can kind of see how that distress changes, and the index pretty much is on a scale from 0 to 100, 100 being good. So you can kind of get assessed that there, as far as their distress index goes, there is cracking happening on the pavement prior to the overlay. IRI is relatively good, getting a little on the high side, but still well within the acceptable range, and very minimal, at least on the increasing direction. We only had about a tenth of a weighted average of rutting, where on the decreasing direction is a little bit almost twice that. So again, not terrible amount of rutting. IRI good, and as I said, both of the increasing and decreasing direction have a distress index showing, so they do have cracking occurring prior. For this, the Michigan DOT uses an initial IRI of 67. Terminal of 172, and again, similar as far as the reliability goes. Does use 50% now for thermal cracking, as it does with the AC over AC. Again, similar, the default values for thermal cracking as well as total thermal plus reflective of 1,000 and 2,500. Top-down cracking of 25%. I mean, a lot of the very similar. And here, Michigan says, hey, we're not going to, we want to know if our design exceeds 15% of the underlying cracking of the JPCP is still occurring. So there's a way there that they're also aging the distress in the JPCP, much like they were doing with the asphalt. The existing pavement does continue to fatigue with time. All right, and here in the similar case, we've got the AC overlay. The existing asphalt is 2 inches of asphalt, 2 layers of asphalt, I should say. One is 2 inches thick, the other is 3 inches thick over the 9 inches of JPCP. There is a 4-inch aggregate base, 10-inch sand base under that, and it's sitting on top of a clay subgrade with a liquid limit of 33 and a plasticity index of 15. And again, we're using a asphalt overlay of a JPCP and looking at a 20-year design life. The original was built in 1961 with the new asphalt, that would be the concrete, the new asphalt being placed in 2023, so another couple of years after the 2019 date. So that obviously the pavement continued to deteriorate between 2019 and the intended overlay of 2023. All right, similar to the asphalt over asphalt, there's this traffic inputs, and again, I'm just kind of showing this just so you guys get an idea of what information was used. So two-way ADT was about 7,900, 51% split, 51-49% split in the direction of traffic, and then 92% of it is in the design lane for this analysis. And then again, the DOT did not put a traffic capacity cap on the analysis. Growth rate in this case, again, this is going to be very much highway specific, but in this case, the DOT is looking at a compound growth rate of 0.75% for all vehicle classes. The distribution now here for this road is different depending on the type of class or the class of truck as well as in the month. And I'm only obviously showing you through August just for simplicity, but it obviously there are, for the remainder of the months, there is a similar type of variation in traffic. So again, it's based on your traffic information that you get, and again, hopefully this is very much in a database so that nobody is typing in all this information, which I know the majority of DOTs have traffic databases. That's a good thing. Similarly, as before, be able to vary the class of the class of truck by single, tandem, tridem, and quad, and being able to put that information in. So that's also pretty standard equipment, pretty standard information. Here again, being able to pick a location of the project in Michigan. Again, we had it slightly different than what was provided, but it's still it's pretty close, the information that we were able to grab. All right, so different from the AC over AC, the AC over a JPCP, you need to be able to go in and include the design properties so that we know what the dowels that were used in the jointed plain concrete pavement, what was the joint spacing, all that type of information is actually needed to be able to help in some of the performance prediction, and certainly for quantifying the continued damage that occurs in the JPCP layer. So here we're just looking at dowel joints. The original was built using 1.5 inch or 1 1/4 inch dowel bars at a 12-inch spacing. And then looking at erodibility index. Again, this is an assessment of the material underlying the concrete layer. Is whether or not you have full friction and what is that loss of friction and how many months does it take. Whether it's a bonded or unbonded, I think it's unbonded. Unbonded JPC was a false in this case. Otherwise, you say obviously it's true. Going through on the joint spacing, you can actually identify if it's uniform or if it's random spacing. And in this case, it's going through and showing that the joint spacing is at 14 feet. But again, if you had that variable, you could put that in if so be it. Looking at curl and warp. Again, these are default values as far as the -10. Being able to put in the sealant type, there's a couple of options. I didn't showcase what those were, but certainly it's the ability to select that, and then whether or not you have a tied shoulder. And in this case, there is no tied shoulder. And then whether or not you use a widened slab. And again, in this case, a widened slab was not originally constructed. All right, so similar to what I showed on the AC over AC, here's the properties of the existing layer. And in this case, we actually did run it as a separate, the two layers as separate. You can see the only difference between the original, the two, so how do you put this? The existing layer, I'm actually sorry, I am going to take that completely and totally back. The overlay, I think I had an error maybe in my layer screen that actually the existing is just 3 inches on top of the jointed plane concrete pavement. And then as part of the rehab, it was a two separate overlay. One is 1.5 inches using the information you see here. And then the second one, or so the first overlay was 10 inches, or was 2 inches. And then they overlaid that with a 1.5. So total overlay of the existing composite pavement, and I am sorry guys, is 3.5 inches. So just to get that clear, so I got to go back and fix my original slide there. All right, so total 3.5 inches of overlay in the new design process. So that's what we're gonna go with. As far as the base layers, and again, I didn't go through all the inputs showing you those screens because they're very similar to the ones used for the asphalt over asphalt. And so on the base and subgrade layer properties, again, very similar as far as the coefficient, or very the same as the coefficient of lateral earth pressure that was used in the AC over AC. These are default values, so that makes perfect sense. But showing that for that non-stabilized 4-inch base, it was a A1A soil with a resilient modulus of 33,000 psi. The sand subbase at 10 inches was 20,000, and then sitting on a somewhat soft subgrade with the PCI or PSI of 5,000, again, which I think would be typical of what we would expect for a clay type of subgrade. All right, so this is just to do my little check to make sure that everything is doing as I expected. And so this shows that existing overlay is 3 inches with the 3.5 on top. Perfect, that's what we wanted. And then the original heavy trucks is 7,900, and then that progression over the 20 years to see the 29 million by the time we get to 2043 as far as the cumulative trucks go. All right, so similar to the AC one, I went ahead and said, okay, what happened if the original design by the DOT was this 3.5 inches, and they repaired 2% of the 10% of distressed JCPC slabs prior to the overlay. And I said, okay, well, let's see how the impact of what you repair versus what you remain distressed, how that impacts. So I did a comparison of having 10% distressed slabs, and I'm not going to fix a single one of them, versus having 10% distressed slabs, and I'm going to fix every single one of them. And you can just kind of see how that varies the performance and what that impact is. And then again, I really didn't think going through and changing the binder was going to solve some of the reflective cracking that actually is occurring. So I just went ahead and said, hey, you know, rather than this 3.5 inch overlay using the PG 6428, I just said, hey, you know what, I'm going to put down 2 layers. One of them is 2 inches thick, the other one is 3 inches thick. So essentially just almost just increasing the asphalt thickness and seeing how that impacts the performance results. All right, so looking at just the slab repair. So again, this is looking at, I've got 10% distressed slabs. I'm not going to fix a single one of them. Everything as far as IRI, the rut in the asphalt layers all look good. The bottom up cracking looks great. Nothing happened there. However, we've got quite a bit of transverse cracking. Our target was 2,500, and we're 3 times that. And so same with the thermal cracking, we're seeing quite a bit there as well. And as you'd expect, the JPCP transverse cracking, we didn't do anything to 8% of those or to 10% of those slabs. And so, sure enough, they're all going to continue to cause problems. They're all going to continue to crack. And so it's not unexpected that our target was 15, but lo and behold, it's, the predicted value is 24. Again, that's no surprise. I fully expected that to happen. All right, so what happens if we go ahead and say now we're going to actually repair 2% of the 10%, so the DOT design in this case. And again, this is using their 3.5-inch overlay in all of these cases that I'm showing you here. So I'm just changing the slab repair portion of it. We really didn't do a heck of a lot as far as total transverse cracking goes. The thermal cracking, it was unchanged, and we slightly improved the JPCP transverse cracking, went from a 24 down to only 21%. So we did a slight benefit there, but again, still not very significant. All right, from here on out, now becomes the cost estimate, and so when you're doing these designs, or at least when I was doing these designs, I didn't take into consideration the cost. So what happens if I fix all of the distressed slabs? So there's 10% distressed, and I'm going to fix all of them. Didn't expect to see a big difference in total transverse cracking. Didn't expect to see any change in thermal cracking, because that's still not, you haven't done anything to stop that, right? You still have concrete joints, you still have, that type of process is still happening. But lo and behold, you fix all your JPC transverse cracking problems. Again, that's totally expected, and I guess it's good to know that if you fix everything, the program says, yep, you fixed everything, and so you no longer have a JCPC transverse cracking problem happening on the pavement. So that was actually just a confirmation that what you think would happen actually did happen. So that was kind of a good thing. All right, so what happens, oops, sorry about that. So what happens if I say, you know what, I'm going to change the overlay thickness? And so what I put on here is I left fixing everything, because fixing all the distressed slabs. Again, I had to pick one, so I went ahead and picked that one, just so that we can more focus on the impact of total transverse cracking and thermal cracking, more so than, hey, we still have a transverse cracking problem in the JPCP. By going to a 5-inch overlay versus the 3.5-inch overlay from the DOT, we actually improved the total transverse cracking as well as the thermal cracking, but not significantly enough to meet the target criteria. So it's still, we're still twice the amount of transverse cracking that we wanted, and twice as much thermal cracking. So again, you're not going to solve some of these problems in thickness alone. And again, I know that's something we kind of continue to discuss. I mean, even with the AASHTO 93 guide, I mean, you never can solve all your problems by a thickness increase. And so that, again, it still holds true, and that you shouldn't be going through and trying to get rid of something by increasing the asphalt thickness, because I can tell you won't. I believe I didn't try running it thicker, but I think it's something that is probably, you've got to do some other type of mitigation efforts to be able to handle that, as well as knowing that if in your agency, so Michigan maybe says, you know what, the 1.5 or the 3.5-inch overlay actually helps mitigate transverse cracking, then that's going to show up in your calibration effort, right? So again, these are using the global values, but in your instance or in your agency, if you say, you know what, I know that doing a 5-inch overlay of a JPCP or a composite pavement works, then you got to go with what actually works, and hopefully that's shown in your calibration effort. All right, so I said, you know what the heck, let's go and let's make it a 6-inch overlay. Again, I don't know that probably cross slopes won't handle that. You probably have to worry about adjusting a lot of the access roads and worrying about how you get people off of a 6-inch overlay for safety. But I went ahead and did it anyway, just to show you that you can't overcome the amount of transverse cracking, thermal cracking by thickness alone. So again, I've doubled the asphalt overlay thickness almost, and I'm still not there. I'm still twice as much transverse cracking as I want, and still haven't really made much of a dent on the thermal cracking. So that really is just a kind of a, I did it knowing full well that it wouldn't, but I wanted to show that it still is a problem that you've got to be able to overcome in some other fashion rather than just thickness alone. All right, that was probably even quicker than the AC over the AC. So Kelly, do we have any questions?
We do have some questions, yes. Let's start off from the beginning. We have, the first question is, do you recommend using average or weighted average distress values as input values? That's a very good question.
So this kind of gets back to a pavement management question. So if by chance you have an absolutely perfect road sandwiched between pavements that's falling apart, I would not use average, or even a weighted average for that matter. I think if you have performance that is drastically different throughout the project length, I would absolutely go through a segmentation process and try to identify locations. Now, if they're not statistically significant, you could probably just go ahead and do a weighted average. But I would just, I'd refer back to like a pavement management type of approach. Significantly different, you should evaluate them separately.
Very good. Another question is, were you using statewide average truck data, or were those site-specific values?
I believe, and I'd have to go back to Justin on this, but I believe it is site-specific.
And Justin just weighed in and said it's clusters. Cluster information.
Okay.
Yep.
Thank you, Justin.
And PTRs. Lydia asked, I may have missed it, but what drives the thermal cracking?
You didn't miss it, Lydia. I didn't talk about it. I'd have to go back and get back to you on that one. It's obviously it's temperature. It's obviously a lot. I don't remember. Let's be honest. I don't remember. Let me get back to you on that one.
I think in a lot of cases, it's the binder. You got to get the right binder for the climate that you're in. I know that's something that we've run into a number of times. Here's a question. How do we model existing JRCP overlay or composite with JRCP?
Oh, you don't. JRCP is not included. So you'd have to make some assumptions and model it. You're kind of stuck. You can't really model it as a JPCP, and it's certainly not quite a CRCP. So you'd have to figure out a way to maybe modify joint spacing, maybe based on the amount of cracking that you have on the JRCP. I don't. It's difficult because the other tough part, of course, is the prediction is going to be more a function of the JPCP and CRCP and has nothing to do. So the aging of the JRCP is probably going to be very inaccurate because it wasn't included in the LTPP, and so it's not included in the design procedures. So you'd have to make some estimates, and I think you could probably go through and say, hey, I'm going to model it as a JPCP, see what happens, and then maybe model it as a very stiff base layer and just put asphalt on top of it and see what kind of a results you get.
Very good.
But you won't be able to help with that reflective cracking that's going to happen. I mean, that's like, again, I think you'll find that you can't overcome reflective cracking anyway with just asphalt thickness.
Right. Okay. Another question is how to consider the existing distresses, rutting, cracking, etc., in the existing 3-inch AC layer over PCC. In your case, it seems treating the existing AC layer as a new layer, which seems not the real situation.
I don't know that I don't know that the 3-inch layer was treated as it was treated as an existing layer, not as a new layer. So the new layer was the 3.5, the 1.5 plus the 2 inches
Yeah.
of new over the existing 3-inch layer.
Right. Maybe there was some confusion on the layers there.
Oh, I didn't cause that, did I?
No, I don't think so.
I think I did.
Okay. Maybe a couple more questions. Has anyone tried a binder-rich intermediate course brick over concrete pavement? It looks like maybe there's been some discussion about that in the questions box. Let's move on. Here's a question. Is there any FWD testing data used to characterize the existing HMA and unbound layers? I believe we were just looking at kind of the distress approach to the design, right?
Yes. We didn't, you know, and Kelly and I actually talked about that. We really didn't dive into the whole FWD coordination, going through and using the back calculation tool. We kind of decided let's focus on the stress, you know, the rehab option level 2, rather than getting into the whole back calculation. Because I know Harold has covered that in a couple of different webinars, but certainly if that, you know, ends up, you know, floating back to the top of the group, that's something that maybe in a future webinar we can address a little bit more.
That's right. And I know Harold has done a couple examples in the user group meetings in the past, as well as some of the AASHTO aware webinars. So good question.
Right.
Let's see. Another question. Within the JPC rehab tab layer, input is required for slabs distressed/replaced before restoration. What exactly does this mean?
So it means is how many of, so they're making the assumption that you have, or you have none, right? So you can either have distressed slabs or you don't have any distressed slabs. So that's both it's an input. So what it means is that you have an underlying fractured slab. So you need some type of a slab replacement in the existing JPCP. So underneath the existing asphalt layer. So you've got, you know, it's a transverse crack that is reflected through the existing asphalt layer that you know is distressed from the underlying jointed plane concrete. So it's a matter of going through and being able to remove the asphalt layer, remove that or repair the concrete slab prior to putting down the new overlay. So it's really an assessment of the amount of additional distress that occurs in the concrete layer after placement of the new asphalt overlay. So it's very similar, like in the asphalt over asphalt. The existing asphalt pavement continues to fatigue, continues to age, and that fatigue and that aging does have an effect on the overlay. So it's similarly with the AC over the JPCP. The underlying JPCP continues to have, you know, load impacts, continues to distress, that's transverse cracking type of information, of the distress, and that is going to reflect through both the existing asphalt layer as well as the new asphalt layer. And so it's really capturing the fact that you've got, you know, broken slabs and you haven't repaired them, so they actually continue to fatigue and have a problem with the new overlay.
Yeah, and I'll just add that really it's kind of a trade-off, because by fixing the slabs before the overlay, you're adding the costs to the construction, but you're also reducing the thickness that's required, versus if you didn't do any repairs, then your thickness requirements on the overlay would be greater. And you're looking at the life cycle cost part of it. So there's some trade-offs as part of the costs. All right.
Well, it's to capture what we know is true, that if your concrete continues to fail, it'll impact your asphalt overlay.
Exactly.
So, yeah.
All right. There's a couple more questions in the box, but I think we're going to move on, and we'll let Julie tell us about design of AC overlays on fractured concrete pavement. Thank you, Linda, for your topics.
Thanks, Kelly.
And Julie, do we want to go ahead and do a couple polls now?
Yeah, that sounds like a great idea, Kelly.
Okay. So I'll rely on Prashant to post those for us. Can you get those up for us, Prashant? Excellent. So now we're looking at fractured concrete pavements and the overlay of those types of pavements, and looking at kind of the crack and break seed approach versus rubbleization. And this first poll is looking at overlays on crack and break and seat projects. And we're doing these poll questions just kind of to supplement what we do at the user group meetings. I know when we do the annual meetings, we have a pre-survey before the meeting and get your inputs on different implementation aspects and design aspects. And these questions are a little more penetrating, a little more pinpointed to the specific designs that we're covering today in this webinar. So, but we did want to put these out there and get people's responses on it. How are we coming, Prashant? We got a good percentage of responses?
Yeah, about 60% response rate. I'm going to put up the next poll question right now.
Okay. So now we want to know what your experience is with overlays and rubbleization projects using PMED. How are we looking, Prashant?
Almost 60%, but not quite there yet. Gonna give it 5 more seconds to see if more people would chime in.
Okay. All right. Thanks everybody for your responses. And now we will turn it over to Julie. Julie, you have the screen.
All right, thanks. I think a couple more seconds here. I'm not sure that I've been provided with the possibility to present.
You should have access, Julie.
Yep.
Okay, it just came up. Thank you. All right, you can see my screen now, I take it?
We can.
Okay, so are you looking at the audience mode or the presenter mode?
Looks like presenter mode. We see 2 sets of slides. So there you go.
Thank you. All right, well, thanks a lot. And first I want to thank Lydia Petticord with Pennsylvania Department of Transportation, and Tom Adams, who was formerly with PennDOT, as well as Greg Tommen from Lindy Paving, in providing the project. And as I knew Linda would do and did do a great job in talking about how to define the inputs. A lot of them are similar, of course. So I'm going to focus mainly on the inputs for fractured concrete pavements, and the focus is on how to interpret the project such that you can define the input. So thanks again to Lydia, Tom, and Greg for providing the opportunity to do that. They presented the project information with some great design information so that I was able to do that. And again, this will be crack and seat slash break and seat and rubblization. And just kind of a review, and I saw in the poll questions, very few people are using Pavement ME for designing these types of pavement structures. And maybe that's because they don't do a lot of this type of a pavement structure, but hopefully through this presentation, maybe you'll have a better feel for how easy it is to use Pavement ME as a design tool for these types of pavement structures. So just crack and break and seat, are the same thing, with the exception that break is referring to a jointed reinforced concrete pavement where you have reinforcing mesh in there. And so you don't want to just crack the pavement structure, but you also want to rupture that steel. So the project that we're going to be talking about is a jointed reinforced concrete pavement. So I'll be referring to break and seat, which just infers that you're going to rupture the steel when you perform your demolition of the slab. So in crack and break and seat, of course, that's larger fragments where you want them 1 to 2 square feet in size. And these pieces are then seated in. So you fracture the slab and then you seat it into the underlying granular layer. And then rubblization is where you're just going to rubblize this into more of a nice aggregate base. And so those particle sizes are 3 to 8 inches when we refer to rubblization. And the big thing too is in Pavement ME, when you're designing a crack or break and seat, then that's designed as an overlay, and then the subcategory of AC over JPC fractured. Whereas if it's a rubblization, even though you're still putting an asphalt overlay per se on top of it, that rubbleized layer is just working as a nice unstabilized granular base. So it's designed as a new pavement under the flexible pavement option. And the big thing too to remember is that when you're performing this, you want to make sure that you're debonding the steel from the concrete. So the idea is that you'll have nice aggregate interlock in between particles, regardless of whether you're rubblizing or doing the break and seat. So what I was going to do with the project that PennDOT was nice enough to provide the information on is first talk about it from a break and seat perspective, and then look at rubblizing. So when we're looking at break and seat, crack and seat, break and seat in this situation, the design inputs that that we're looking at that's more closely affiliated with specifically a break or crack and seat is looking at the performance criteria, where you're looking at the AC total transverse cracking, and that's including thermal plus reflective. And the design criteria has thermal pull out separately, but also then thermal and reflective, where you have the concrete underneath that, the distress in that concrete reflecting up. And hopefully, again, the whole idea of the break and seat or the rubblization is to make sure you're not getting that reflective distress. So in the design type, as I just briefly mentioned, for the break and seat, then that's going to be an overlay design, and you're going to then select the subcategory of AC over fractured jointed plain concrete pavement. And then, this of course is a jointed reinforced, and there's a question that came up regarding the difference of that before, but it's going to be the same, and you want it to interact or behave the same underneath it if it's a crack and seat or a break and seat where you have the reinforcement. So both of them, again, if it's jointed reinforced, you want to make sure that you're debonding that concrete from the steel, so then they'll act similarly or in a similar manner. Okay, and then climate, the same thing that I believe Lydia mentioned, and those of you familiar with Pavement ME at this point, the asphalt component was calibrated using the mirror data, so that's what you're going to want to use when you're doing a break and seat or a crack and seat design. So when we get to the layer of the fractured concrete, there's a couple of inputs that you want to define, and that's crack spacing, and that's going to be a range recommended of 1 to 3 feet that you'll want to select within. and then the fractured slab load transfer efficiency. So as we had mentioned, we want these segments to be fractured, but we want to have interlock in between them, aggregate interlock, so that it's engaged in transferring load, which of course helps prevent reflective distress. So then the load transfer for efficiency recommended between these segments is 30 to 90%. The unit weight is just typical of that of concrete and Poissons too. And then the elastic modulus, the suggested range, and I apologize, I forgot my units here, is 150 KSI to 1,000 KSI. So 150,000 to 1,000,000 PSI is what is typically recommended, and we'll talk a little bit more about that later. Okay, so going into the project itself, the location of the project just coincidentally happens to be right outside of Pittsburgh, Pennsylvania, which of course is where I'm located. So this was kind of nice to have it nearby. Provides me with a better understanding of the site conditions. But as a 13.7-mile section, again, it was jointed reinforced concrete pavement. So you can see the city of Pittsburgh here, and then this was just northeast of that a little bit up the Allegheny. So the project history then, this existing concrete pavement, reinforced concrete pavement, was constructed in 1984, 25-foot dowel joints, and there was concrete pavement restoration performed in 2009, and then again in 2004, and then the break and seat was performed in 2021 in a 35-year design life was used. This CBR for the subgrade in this region, Pennsylvania uses the California bearing ratio, and that was 3 to 5. So of course the support condition, is a relatively soft subgrade, which is always a point of interest when you're trying to do a break and seat or crack and seat or a rubblization. And obviously you have to impose a lot more energy into the slab if you're going to do a rubblization. And it's hard to do that with such a soft subgrade, and I believe that's why PennDOT chose to go the break and see route as opposed to rubblization. So there wasn't a lot of information regarding the distress prior to the overlay, but as you can see, there was a lot of patching, and again, it was noted that this was done in 2004 and 2009. So extensive work on the roadway prior to this. As you can see, it's a 4-lane divider with 2 lanes per direction, and the speed limit in this area is 55 miles per hour. So additional information regarding the traffic, relatively small. It was noted that there's still kind of a better feeling for easels, and I'm the same way, and so I reported the easels here as estimated using the Pavement ME. And so it's not a lot of traffic. The design lane had about 12 million easels, which is about 17 million heavy trucks. For those of you that aren't familiar, the nice thing about those analysis folders produced by Pavement ME is it does provide you with a lot of great information in there that's not necessarily depicted in the output file in the PDF, but one of those is the easel count. I think that's in it's labeled flexible easels. I think it's an Excel file, but all of the files in there you can usually look at either in Notepad if it's a text file, or in Excel, and they have a lot of great information, and I would encourage you to kind of peek in there and see what type of information that you can get out of those files. Or there's a lot of interesting stuff. Like I said, I do still look at both easels and heavy trucks when I'm looking through this, and that provides, you can find the easels in those files in the analysis folder. All right, so the current structure, this JRCP was 10 inches thick. and that was on top of 12 inches of a dense grade sub-base. For those familiar with PennDOT materials, it's a 2A, which again is a nice densely graded sub-base material. The subgrade was classified as a A-2-4. And even though this is a webinar on Pavement ME, you know, regardless of what design procedure I'm using, I typically try to look at a couple of different design methodologies, because they all have different development, you know, they're based on different theories and using different data to develop them. And so I always find it interesting to see what the other ones, but it also helps me interpret the results of each individual design procedure. So the nice thing was Tom Adams, again, who was formerly with PennDOT, did do this design for this roadway using a couple of different procedures just to get a feel for things. And he used the 93 guide, and that came up with 16 inches of asphalt, which of course is quite thick. And so he looked again a little bit further at the frost heave, and used a different predictor for the CBR, or the resilient modulus based on the CBR, and was able to get that down to 8.5 inches. But you know, obviously that's a big jump, and so they're trying to get a bit of more comfort on going that thick, and so they used the Napa rubblization design guide, and that came up with 8 inches. And then they talked to several other agencies. I understand, I think Tom had mentioned he looked a little bit at what Illinois was doing for something similar regarding the level in traffic and the site conditions, and they had some pavement structures out there where they did break and seat, crack and seat type of a rehab with 8.5, and they felt that they got some you know, their expected performance out of it. So just a little bit of background regarding what values they came up with outside of Pavement ME, and then just jumping into the Pavement ME itself. So with Pavement ME, and again, this is the brake and seat design that I'm going to go through now. And as we had mentioned earlier, the design type is an overlay, and then it's AC over JPCP fractured. And again, the question came up before regarding whether it's a JPCP or a JRCP. That's just one option. And even I guess with a JRCP, if you're just putting an overlay right on top of that, and Linda had mentioned that you can probably just use a jointed plane. And if you do have ruptured steel at mid slab, so for example, this would be a 25 foot, and you found that, you know, most of it had ruptured steel, you could just make it a, you know, a 12.5 foot joint spacing, and that might get you something in the ballpark. But for this, again, it doesn't really matter, because you're going to fracture it into small fragments regardless of the size. So again, the design life was 35 years. The base construction, which for this, the base is now that fractured slab. So you put in the construction date when that jointed reinforced, in this case, was first constructed, which was in 1984. And then the pavement construction would occur in 2021. So the traffic, again, I'm not going to go through traffic inputs. I think, you know, Linda did a good job describing that, and you're probably pretty familiar with that at this point in how to do that. But the traffic, as you can see, is not very high. The capacity wasn't enforced, but of course it's nowhere near capacity, so that's irrelevant. But only about 2,000 trucks a day. And so again, not a lot of traffic, 50% in each of the design directions, and 90% of the traffic was assumed to go in the design lane. And again, that equated out to about a little over 12 million easels throughout that 35-year design life, and 17 million heavy trucks. Again, climate, the mirror data, of course, was used in the site in the Pittsburgh area. And I think at this point, that's similar with all of the other payment ME designs. So I won't go into the details, but just to give you a feel for what the climate is in this location as we look at the different types of distresses that develop. We do get to, of course, some winters in snow, but it comes and goes relatively quickly. So we have a lot of freeze-thaw cycles and not really a deep freeze. We do get a lot of rain, so there's a lot of precipitation. Okay, so and then going into each of these existing layers, and the brake and seat layer is what we see first. And you'll see that the crack spacing that's selected by PennDOT is 2 feet, which was right in between that 1 to 3 foot range. But they also, in their construction, do have some definitions on exactly how they want that fractured. And so they use that, I believe, to help define this input. The fractured slab, load transfer efficiency, again, this was in between the 30 and 90%. You can use the FWD to get an estimate of that potentially, but based on this design, it really didn't have a big influence on the predicted distress. Now, the same thing with the strength. If you're going to subdivide this into 2 layers or 1 layer, you can define the strength by back calculating deflection information. But of course, then that has to be done after it's fractured. And as you'll see, I think one of the nice things that PennDOT does is that they do have that as part of the criteria. So if you define a value that you want, then they can do the back calculation during the construction process to make sure that's being achieved. And I'll show you in a couple of slides that that's what PennDOT does. The other nice thing in doing that is you can start developing a database based on how they're fracturing the slab. So in this instance, it was using a guillotine, and the results that you have with respect to the resulting back calculated value that you would achieve, because obviously you're not going to be able to measure that prior to the construction. But if you can start getting a feel for what these values are, then it'll help you in future designs. And then I do think that Lydia was on there because she had a comment or a question. So that's nice as well if we have any additional questions that she might be able to help us field. Okay, so regarding the 2A subbase, this is a standard material again for PennDOT, and this information is available in their materials library. So for this design, it was about 23,000 PSI for the resilient modulus used. And then for the subgrade, again, the CBR was around 3 to 5, and the resilient modulus for this was 7,500. So, just you would define these parameters just as you would with any other design that you're using that's not associated with a crack and seat or a break and seat. So just common practice. So with the overlay, the asphalt that's on top of this break and seat, PennDOT typically uses 2 or 3 layers. Here they had 3 layers of wearing, a binder, and a base course, where we had 1.5 inch of the wearing, 2.5 of the binder, and then the base was 4.5. So with this pavement, which again is a common structure that they have, and they use the level 1 inputs from the materials library that they have for these materials. And again, Linda went over defining the level 1 inputs, and so I'm not going to spend time doing that again here. All right, so then we ran the analysis, and this is what the results were. So the targeted values that you see are what PennDOT typically uses. And you see with the what failed was this thermal cracking and reflective cracking combined. And again, the thermal cracking itself, I think if you drive around Pennsylvania, you see that that's not really a big issue here. And you're going to correct that type of a thing based on a binder, not increased thickness. And just as Linda had mentioned, increasing the thickness of that overlay did not help with eliminating the reflective cracking. And I went quite high. I think I went up to 20 inches and it still wasn't able to meet that. But, you know, the other thing that you can adjust is your load transfer efficiency that you assume between the particles and the distance between the cracks. And remember, we selected 2 feet here, but neither of those were helpful in changing that either. So this was the final design that PennDOT moved forward with, and I kind of see why they would feel comfortable with that. So again, this isn't part of the Pavement ME inputs, but I think it helps with respect to the design philosophy. So when they constructed this, they required that, remember we talked about the brake, and is the brake component of it is to make sure they rupture or sever that mesh. And the subgrade's relatively soft, so one way to ensure that this occurred was that they did do saw cuts at 1/3 points of the slab, so they could guarantee that the steel was no more than 8 feet of a stretch before you would have something completely ruptured. So they did do that with this section. They also used the guillotine breaker to fracture it. And when PennDOT does this, they have a 250-foot test section that they use, I believe, to make sure things are going according the way they would like prior to going on with the rest of the project. So with the guillotine, they wanted the brake pattern to be every 18 to 24 inches apart, so every 1.5 to 2 feet. And then the back calculated value they were targeting was 400 to 900 KSI, and they were verifying this with the FWD. So after that, then they seeded it with the 50-ton pneumatic tire roller, requiring 2 to 4 passes. This was the project. As you can see, here's the guillotine that they used to fracture the pavement, and then you see some FWD testing. And again, thanks to Tom from Lindy Paving, or Greg Tommen from Lindy Paving, for providing these photos and a lot of the information on this aspect of it. So they would do the FWD testing and then ensure that they were getting the E values that they desired. This is a cracking pattern that was achieved, and I think Greg said that this was actually from 79 possibly, and not 28, which is a road nearby. But you also see the core that they take to make sure that the fracture is going full depth. You also note that there's good aggregate interlock along that fractured particle. So they are getting good aggregate interlock within that layer. And again, they used a 50% load transfer efficiency, which I think is probably a pretty realistic value. So the nice thing about doing that FWD testing, of course, is it provides you information regarding if you're achieving the inputs that you use in Pavement ME, but also gives you future information for what you can achieve. So when you're designing these inputs on other sections, that becomes valuable information. And then they're seeding it here, and there's the final product. So again, the whole idea of just kind of going through some of the things that PennDOT does, I think it's nice because it sort of gives you a closed loop system. You can't really know the elastic modulus ahead of time, but you can know what the target value is and know what you're achieving by measuring it on that test section that they have. All right, so again, they chose not to look at rubblization on this project because I believe because the CBR is so low and it would be very difficult to rubblize this 10-inch DRCP on such a soft subgrade, but I still wanted to use it as this design example since we had a lot of great information. Going back to what we were talking about before regarding design inputs that are associated specifically with rubblization, in focusing on those, you had the design type, and again, it's an overlay in a sense, but it's treated as a new pavement, a new flexible pavement, because that rubblized layer is treated as just a granular layer beneath it. So for the rubblized layer, that can be either treated as one layer or subdivided into 2 layers, and you can select which one's most appropriate based on deflection data. So the idea is that the particle size distribution is going to change with depth because obviously all the energy imposed in the fractures at the surface. So is there similar properties in the upper and the lower portion of that layer? And typically they suggest if that layer, the concrete pavement's 10 inches, if it's greater than that, then you'll probably want to subdivide it into 2 separate layers. Now, the best way to affirm whether you do want to subdivide it, if that's necessary, into 2 sublayers is to use deflection data. And so if you are doing your back calculation and your root mean squared, you can't get a good root mean squared, something less than 3 with 1 layer, then you may want to subdivide it into the 2 separate layers. And of course, the trick is you're designing this prior to going out and doing it. So again, you could kind of do something like PennDOT does and assume something and then do FWD testing to make sure you're achieving it, but also use that information for designing future projects. And with that, you're not only going to be looking at the thickness of that concrete pavement, but also the support conditions underneath, because that's going to affect the distribution and particle sizes with depth of that layer. Okay, so the unit weight, again, is just a standard of concrete. Poissons is recommended in the manual practice of 0.3 as opposed to 0.2. But I'm sure that's not significantly different. So not a big deal, just part of the recommendations. Now the elastic modulus, instead of being around 150 to 1 million, now you're going to 50 to about 150 KSI. And if you don't know what your value would be ahead of time, which is going to be commonly the case, because as indicated by the poll, a lot of people haven't used this method and may not have a value that they're going to know is representative based on how they do their crack and seat, the thickness and the rubblization, the thickness and the pavement structure, the subgrade that it's on top of, and what will result for that layer characteristics. So pavement ME in the manual practice, they suggest using a value of 65,000 PSI. All right, so again, we're going to go to a new pavement, and we have our recommended values. If we enter them in, we see that the inputs are the same regarding the base is constructed when it was the jointed reinforced concrete pavement was actually constructed in 1984, and then the new overlay will be placed in 2021. So we have a new pavement, a flexible pavement. Again, with this, it's relatively simple now when we're characterizing this rubblized layer. We're going to enter in a resilient modulus, in this instance just at 65, because we don't have a better value at this point to use, but again, we can do FWD testing under a test section to make sure that we're at that when we actually construct the road. So again, using the 3 layers that PennDOT used for the break and seat, and again here, and if we have an 8.5-inch overlay, Again, now we have 10 inches of rubblized layer and then our 12 inches of dense graded base on top of our subgrade of about 7,500 PSI. And this is the results that we get. And so as you see, it looks like we're passing, with the exception of the thermal cracking and also rutting in the asphalt layer. We're not going to design out of that, of course. That's going to be a change in the binder type. But I think PennDOT's pretty comfortable with the performance they're getting with respect to rutting in the asphalt layer and thermal cracking. So I'm not too concerned about those. So that's all that I had to present on crack/break and seat and rubblization. I think we have time for a couple of questions, right, Kelly?
Yes, we do. We have, we got 10 minutes to work with. We do have one question in the poll or in the questions box. And the question is, for the design you showed, number of lanes, should it have been 2 or 4? I think maybe your slides showed 4, but I think it should have been 2.
Yeah, you're right. The inputs, I'm not sure if there was a section up along the way where they had where it was 4 lanes, or if it was consistently 2 lanes throughout that section of roadway. But the input files that were generated had 4 lanes, so I'm thinking that at some point it went from 2 to 4. Again, this is an urban area that kind of connects the northeast suburbs to Pittsburgh, so I'm thinking the number of lanes are changing as you go outward. And it was a 13.5, almost a 14-mile section. So maybe Lydia might have more information on that, but.
Yeah, from what I saw, it looked like a 4-lane, and probably does at some point get closer to the city, probably turns to a 6-lane. I'm not seeing any other questions. There was just some general questions that I responded to in the questions box. If anybody has any questions right now, please forward those. We'll try and have Julie respond to those. We'll give it a minute or a few seconds here.
Again, thanks to PennDOT, this was a great project, I think, to give an example for, and again, Greg Tomlin at Lindy Paving to provide some of the photos.
Absolutely. We again want to thank Justin and Harry and Lydia for providing that information. There's a question here. Did you adjust the stone size of the rubblized layer or assume that of typical dense graded aggregate?
That's a good question. I didn't adjust that, but that should have been done. You're exactly right. Yeah, good point. I'm not sure it would have made much of a difference since you're defining the resilient modulus, but there are aspects that it could affect. Regarding the overall design, I don't think it would have affected it too much, but it's something that should have been done. Good point.
Yep. And then a question, do you recommend underdrain with crack and seat and rubblization? And I know that that's been a very strong recommendation in the past. I think that's still the case. Julie, any thoughts on that?
Yeah, I mean, I guess drainage does help, you know, and I think that most states kind of have, some states have more of a strong feeling on that than others, but yeah, it definitely is a pavement structure that you can get, you know, water to drain out of. So I think it is beneficial.
And just kind of follow up that question. Here's another one. Do you see longitudinal cracking in crack and seat sections? I think that's just probably a general question.
Yeah, I mean, I would guess that you know, that I assume the longitudinally they're referring to top-down fatigue, and it is a stiff pavement structure. So I'm guessing that that is something that will develop. In general, when we were in doing these designs, and I think maybe Linda could probably confirm, but the fatigue in general with these overlays tend to not be the challenge as much as the reflective cracking and the thermal cracking.
Yeah, that's absolutely right. Not really seeing any other questions specific to your presentation, Julie. So maybe we should move on. I thank you very much for giving that presentation.
Yeah.
And I guess kind of as we wrap things up here, we did have a couple more poll questions that we wanted to run by everybody based upon today's webinar. So Prashant, can you pull those up for us? Thank you. So a little bit kind of a customer survey type poll question for everybody to look at. And how's our numbers, Prashant?
Almost at the 60% mark. Just crossed 60%. I'm going to give it 10 more seconds and then I'll put up the other question.
Prashant has done this many a times for many other meetings and webinars, and he always likes to get that 65% or higher response rate. So it sounds like we're closing in on that.
Yep. Just hit 65. So I'm going to shut this poll down and launch the other one.
All right. So this one's focusing on the design of overlays on fractured concrete pavement. And there was a question during Julie's presentation about whether we can see the results from the polls, and I put out a response that yes, we will include those poll results with the Q&A responses that we put together following the webinar. So in the coming days, we'll make that information available to everybody.
Almost at the 60% mark, but I'm going to give it a few more seconds and then we can go to the wrap up, Gary.
Okay, that sounds good. All right. Well, thank you for participating in those polls. Just a couple minutes left here, and I just wanted to do a little bit of a wrap up. We do have another webinar that we're going to be putting together here and presenting this fall sometime. We're working through the topics that we want to include in the webinar, and certainly the specific days or day for that webinar, we will come up with that, and we'll put out a save the date and follow it up with a formal announcement about that webinar. Again, that'll be sometime this fall. And at the same time, we're also doing planning of the 2021 user group meeting, and we're looking at November, December timeframe. The format's a little bit, we still need to nail that down, whether we're going to do virtual again or if we're going to do that in person. We're kind of waiting for some information to make a decision on that. So that, again, we'll have a save the date announcement about that, and then a formal announcement, and we'll have put that information out to everybody. So stay tuned with that. Final slide, Prashant. And again, just want to thank everybody for attending the webinar. And if you've got any questions or comments or anything regarding Pavement ME or specifically these designs that we went through today, please feel free to contact anybody and on the project team, as well as Jen Albert, Tom Yu at FHWA. We'll be glad to answer your questions or comments that you might have. So with that, I think we will close it out, and we thank everybody again for attending the webinar. Goodbye, all.